that we've got some refreshments outside here in the room. If you'd like to go on and help yourself. And the fire exit staircase is out to the left-hand side. And tonight we will be hosting a very interesting topic for CPD. It's around the use of Internet of Things, IoT, to monitor and manage concrete durability. This talk will explore how engineers can use real-time data on corrosion, environmental conditions, and material degradation to monitor durability, prevent failure, and do some proactive maintenance, which is very important nowadays to extend the lifespan of our structures. The speaker is Usama Jasir from Pulse Technologies. Usama is the founder and CEO of Pulse Technologies. Pulse is a Dubai-based pioneer in IoT solutions for structural durability monitoring. Usama is a chemical engineer by education, and he's got over 30 years of experience in durability engineering. He has published several peer-reviewed technical papers with the ACI and the AMPP, and he has contributed to many iconic projects here in the UAE, like the Burj Khalifa, the Expo 2020, the Sustainability Pavilion, and many more, which we were just discussing before we started today. And this is where he applied his expertise in corrosion control and infrastructure protection. That's all for me, a quick introduction. I will now hand over to Usama to take you through his presentation. Thank you. And we'll take the questions at the end. If you don't mind, please keeping the question till the end. We will take them either in the chat box of Zoom or here in the room. You can just raise your hand. Thank you.
Great. Thank you, Iman. Thank you, everyone. Great to see you here. Great to be here with you at iStruct. It's a pleasure. Thanks for those who are here beating the traffic to be with us. Many friendly faces. So tonight's topic is maybe on the fringes of structural engineering. We're going to talk a little bit of chemistry. We're going to talk a little bit of electronics. But it's all related ultimately to the structural integrity of our built environment. So our topic is IoT for durability monitoring. To start with, what is IoT? IoT is the Internet of Things. Let's see. Okay, so Internet of Things. When Internet started, it was connected to our PCs, our laptops. Bit by bit, it started creeping into everything. It got into our phones. Next, it got into our wearables. I'm wearing a Whoop, a wearable device that tells me about my stress and strain. It tells me about my sleep habits, my deep sleep, my REM sleep, my recovery. So much data comes out of this little device on my hand. Internet is connected to more and more things and giving those things superpowers. Cameras today, security cameras, are connected, streaming the images directly to the cloud, providing us with real-time visibility of what happens, alerts, facial recognition. A lot of superpowers are added onto normal devices. So where does this come into our realm of structures? So we start out with the challenge. What is the challenge here? The challenge is that civil structures age. And just like with us humans, with age comes declining health. Only buildings, bridges, tunnels, they don't tell us when they feel those early symptoms. We find out about those currently through periodic inspection. So periodic inspection happens every 2 to 5 years, depending on the client, depending on the regulations. And to share with you the output of what RTA looks at, for instance, here locally, they do regular inspection of their assets, and then they categorize those assets from 1 to 4, 1 being good, 4 being critical. Good is described as the element shows no deterioration. Shows no deterioration. It implies it's visual. It's a visual inspection. Visual inspection tells us what's happening on the surface. They don't go beyond that. Go a step further to fair, minor cracks and spalls are appearing. So already we have cracks and spalls that require repair. That's the extent of what visual inspection can inform us. One of the other challenges of periodic inspection is access limitation. Sometimes you require special access equipment to be able to reach the areas requiring inspection. And there are underwater structures that may require specialized divers to inspect and inform us about what's happening visually. We can go beyond the visual using non-destructive techniques, non-destructive inspection. That is usually called upon when visual inspection already tells us there's an issue. Visual inspection uncovers an issue. We go a step further using NDT to find out how widespread is the issue. That's when we'll start looking a little bit beneath. But NDT also has limitations in terms of how inaccessible areas. In 85% of the cases, we find out about problems when they're quite advanced, when they require major repairs. And again, just like with human health, if you catch something late, the intervention is more complicated, the intervention may not be as effective, the intervention is more costly. And that's what happens with major repairs. We're involved in a project in Business Bay we were looking at where the parking has been shut down for repairs. You've been through traffic, those who are here. You know the traffic situation, you know the parking situation in the city. When the parking is shut down for repair, that's a major disruption for the tenants of that building. That's a major reputational disruption for the landlord of that building. So repairs, when they're major, are quite disruptive and costly. Sometimes we uncover things a bit too late. These are actual cases in Dubai. This is a headline from local newspaper. 10-year-old buildings face demolition. Over 400 homeowners uncertain about future. Expert committee finds structural defects, severe corrosion, which requires direct and rapid intervention. These things are real. It does get to that extent. This is a collapse that happened in Dubai Marina. Corrosion was one of the causes of this collapse. So it gets this bad. Usually we have early warning. We have signs, even with visual inspection, that could inform us before it gets that bad. But still, these things happen. So to talk about our topic, IoT. IoT in structural engineering is not something new. It's been around for decades under the name of structural health monitoring. Structural health monitoring is a strategy for detecting, monitoring, and predicting the health of civil structures, ensuring their safety, durability, and efficiency. This is a definition from a Syria guide, Syria C788. It's a guideline for structural health monitoring in civil engineering. This guideline was written by a group of experts in the field from different consulting companies. I'm not sure if anybody here is from AECOM. AECOM was the lead in this. Mott MacDonald participated. Some people from Mott, some people from Bureau Happold participated. So if you look at the guide, hopefully you'll have it in your libraries. It lists the different individuals, the experts who wrote this. And there's a lot of valuable information in this guide that provides insights into the different aspects, including the deployment. So it gives guidelines in the deployment of structural health monitoring. And the starting point of deployment is identifying the quantities of interest and physical quantities. What is meant by quantities of interest? These are the parameters that the engineer is interested in monitoring. But we're not always able to measure the specific parameters that we're looking for. So sometimes we have to derive them. That's the physical quantities. Physical quantities are what we measure. Quantities of interest are really the insights we're looking for to help us with decision making in the future. So for example, a bending moment cannot be monitored. You monitor the strains and derive the bending moment. In the realm of durability, the most important unit is time, because durability is how long can you rely on the engineering properties of a material. So you care about that time, but you cannot detect that. You wind up measuring millivolts and microamps to derive what is the remaining time before failure. So you start out by identifying what you need to monitor, what's critical for that specific structure. Then you move on to modeling what the monitoring system is expected to monitor. So there are theoretical models in all aspects. In durability, we do service life prediction to predict when do we expect failures. And then based on that, based on what we're seeking to measure, we select the technology, what sensor types, what data transmission, all of that. We determine the distribution and sampling rates. And this guide provides some parameters to consider in the decisions. And then there's the specification, deployment, and measurement. Again, this guide has a chapter about specifying how to specify structural health monitoring. There's a chapter about procurement also of the SHM components. So it's an advisable reference if you're interested in moving forward with structural health monitoring. The components of structural health monitoring start out with the sensors. So we've got the sensors, different types of sensors for different parameters. The sensors are connected to a data acquisition hub that collects that data, transmits it to usually the cloud or a server, where the data crunching happens and we get those insights and we can program the alerts and visualization of the data. The sensor types can be categorized into 5 different categories. We've got those that measure load and stress measurement, displacement and deformation, vibration and dynamic response, environmental and exposure, and the topic of today, what we're going to focus on, is durability. Durability is not as commonly used in the industry. We find a lot of structural properties being monitored, although durability is a big thing for structures. It's one of the most limiting factors to the longevity of a structure. So to talk about durability and its monitoring, we start out by looking at what are the degradation mechanisms. ACI 201 defines the different degradation mechanisms for, I'm talking here specifically about reinforced concrete structures. So the durability degradation mechanisms can be classified into structural issues, such as design, construction, mechanical loading, impact, fatigue, incidents that may occur. And then there are the durability concerns that are more environmental or material related. Corrosion, sulfate attack, and alkali silica reaction are some examples. Corrosion remains the dominant form of degradation. A study was done of over 700 different repair projects to look at what was the cause. 55% of them were from corrosion. We also live in a very corrosive environment here in the Arabian Gulf. The Gulf waters are only second to the Dead Sea from salinity perspective. The groundwater is quite high with very high levels of chlorides, which is unique to this region, causing high risk for specifically the substructures. So corrosion definitely is an area of interest, of focus. Before we talk about how to monitor corrosion, it's important to understand how corrosion occurs. Sharing with you this video to walk us through how corrosion happens. So steel in concrete is naturally protected by concrete. The reinforcement in concrete is protected by the alkalinity of the concrete. The hydroxides are formed on the surface of the rebar, protecting it even in the presence of oxygen and moisture. So take the same steel rebar, put it outside, it'll start rusting. Put it in an alkali environment such as concrete, even if you have oxygen and moisture, it's not going to corrode. The problem happens with the breakdown of that passive layer, which occurs due to carbonation, but being in our region where salinity is high, chlorides are the main culprit, and they're the much more aggressive culprit. So as chlorides diffuse through concrete, reach the steel reinforcement, that passive layer breaks down when the chloride threshold is achieved. That's known to be around 0.05% of concrete by mass. When the passive layer is gone, corrosion starts. Oxides and hydroxides are formed, and those have a bigger volume than the original steel volume. And that starts inducing stresses within the concrete. Concrete is great under compression. It is quite challenged with tensile forces. Those tensile stresses cause cracking in the concrete, which leads to more ingress of corrosive species, leading to spalling and and delamination, ultimately leading to structural failures. Now, understanding the mechanism of corrosion allows us to model this process. So we can do modeling of the service life, of the time to failure for concrete structures, reinforced concrete structures, by assuming what is the surface chloride based on data that we have from the field, knowing what the concrete cover is, knowing the quality of the concrete, we can start calculating the profile of the chlorides within the concrete over time. And if we project that over time, we can estimate when that chloride threshold will reach the surface of the rebar and corrosion starts. If we plot that, this is Tutti's model for service life prediction. If we plot that, plot the loss of cross-section of the rebar over time, the initial phase is not affected. As chlorides are diffusing through, the steel is not damaged. There's no loss of cross-section until that chloride threshold is achieved. Once the chloride threshold at the surface of the rebar is reached, corrosion starts and it propagates until it reaches that limit state where cracking occurs. If we go back to what I started with, the inspection, this is where RTA inspectors find out about problems with their structures. It's when cracking has occurred. But a lot happens before cracking occurs. If we're using non-destructive techniques and some monitoring techniques, we can find out about problems at the initiation of corrosion. Some monitoring techniques, which I'll be sharing with you, something that we've developed, informs us before corrosion happens. So if we know before corrosion starts at the rebar surface, we can intervene and delay the onset of corrosion. And by that, delay the whole process of degradation and repair, the whole cycle. We can get ahead of it and be in control of it. To zoom in a little bit more in understanding the corrosion process, I mentioned the depassivation of the steel. When depassivation of the steel happens, anodes and cathodes are formed on the steel surface. This is because concrete is heterogeneous, it's not homogeneous. And the rebar itself, steel, also is a heterogeneous material. So different locations will have different electrochemical potentials. And so you will have positives and negatives and electrons wanting to move. And the anode wants to discharge electrons to the cathode. The cathode picks it up. A surface reaction happens at the cathode surface where hydroxides are formed. And what happens at the anode cycle is loss of metal. The iron reacts with the oxides and hydroxides, and we get the formation. This is where we see the rust product. It's important to understand that because most monitoring techniques, actually all monitoring techniques for corrosion in concrete are based on electrochemical measurements. We look at monitoring and mapping out the potentials to understand what is happening in the steel. So let's move on to the durability monitoring. Similar to all structural health monitoring, we've got sensors embedded in concrete structures connected to data acquisition hubs that transmit the data. And then we have platforms that inform us and alert us of what's happening. To look at the sensor types, there are different sensor types that are available for corrosion monitoring. I'll list them and we'll double click on a couple of them. So there's reference electrodes. These are the most commonly used. They've been with us from the 70s, I believe, reference electrodes being used in concrete structures. Electrochemical potential mapping, this is a unique system that we've developed. I'll talk about that in more depth. Multi-factor sensors, there are sensors that detect multi-factors at different depths. There are 6 parameters: pH, chloride levels, potential, current, resistivity, moisture level. So it's great it's great in providing a lot of data, but it's limited in you can't have too many of these deployed. So it depends on the location that you select to deploy such a sensor. But it has use in combination with other sensors. Anode ladders are also something that's been with us for a while. They provide predictive insights, but they're quite bulky and they use the reference electrodes in conjunction with the anode ladders. ER probes measure electrical resistance. the changes in electrical resistance to derive corrosion rates. They're not often used in concrete, but I'll share a case study where they are also used in concrete. They're more used in oil and gas applications. To look at reference electrodes, start with these since they're the most commonly used. Reference electrodes are references. They're stable references. As I mentioned, corrosion, we have a dynamic nature of anodes and cathodes. So if we have a reference to benchmark, we're able to detect shifts in potentials on the steel. So what we're monitoring is the electrochemical potential of the rebar. So we will know when the risk of corrosion has increased at the surface of the rebar. We won't know ahead of time. We will know when something is happening at the surface of the rebar. One of the advantages is it's standardized as per ASTM C876. There are different reference electrodes. I've got a few samples with me here. So for instance, this is a manganese oxide reference electrode. It's a solid reference electrode that can be embedded in concrete. Cable goes out and you can read the potential between the rebar. So there has to be a lead to the rebar and another one to the reference electrode, and you can monitor the potential over time. It's also used as an inspection tool. This is a version of a reference electrode that's used as an inspection tool. From the surface of the concrete, you can take the readings. This particular one is copper and copper sulfate. So it's a copper metal in a copper sulfate solution that provides stability of potential. So you benchmark the rebar potential versus this. And there's a standardized understanding of the readings that we get from these devices. One of the limitations of reference electrodes is that they drift over time. Because we're measuring potential of rebar of steel in concrete versus a totally different material. Over time, they drift separately. So it becomes challenging to interpret the data after time, and you will have to recalibrate continuously. So you can do that for portable reference electrodes. It's quite easy. So as an inspection tool, it's quite effective. But when it's embedded in concrete, that's a challenge. Calibration is not easy when something is embedded in concrete. It's doable, but it's not simple. Moving on to the electrochemical potential mapping. The sensors that we developed, the electrochemical potential mapping, really maps out electrochemical potential by embedding these sensors. I'll hold one close to the camera for our audience on Zoom to see. So these sensors have different levels of sensing elements. So a series of sensing elements. The sensor is mounted on rebar, on the first layer of rebar. So it is tied to the first layer of rebar. It sits within the concrete cover. As the corrosive species starts coming through, as chlorides start coming through the concrete surface and reach the top sensing element, its potential shifts. This corrodes. It becomes anodic to the rebar. And we monitor that shift in potential. And that informs us that we're getting activity at a certain level in a certain location. We have a second step to also validate that data and validate the insight. So over time, we would expect it to activate, and ultimately the rebar will activate. These sensors are 3D printed to accommodate the different concrete covers that we get in structural elements. So it could be a 50 mm cover, 75 mm cover. We rarely go down below 50 mm. If it's below 50 mm, most likely the environment is not corrosive, and you don't really need to be monitoring for corrosion. But it can be customized to meet the structural element that's in question. One of the main advantages of this method is we're benchmarking steel and concrete to steel and concrete, the same metallurgy and the same material. So drift over time does not occur the way it does with reference electrodes. That's one of the key advantages that allows us to derive insights over time. And it enables predictive insights. Having these steps allows us to discover issues long before they become issues, and be able to predict when would we start seeing damage? So how much time do we have to intervene? Which opens up the options. So this predictive capability is really, we look at the differences, the depth of the sensing element compared to the cover. And it's an exponential relationship. In the fixed second law of diffusion, which is used for service life modeling, the concrete cover is exponentially affects the diffusion of chlorides through the steel. So if, to give an example, to explain this through an example, it's much easier. So let's assume we have a structure that has been designed for a 50-year service life. A durability study has been done based on the diffusion of this concrete mix, and based on the concrete cover, we're achieving 50 years theoretically. The rebar cover is 50 millimeters. The sensor depth is 33 millimeters. The top sensor is 33 millimeters. So cover 50, sensor at 33 millimeters. Theoretically, we expect this sensing element to trigger after 21 years within the service life of the structure. If this gets triggered at a different time, let's say 15 years, we can go back and adjust the service life based on actual data that we're getting in the field. And according to this calculation, this has a 34-year service life. Here I'm showing an example where we uncovered things earlier than they're supposed to happen, but it could be the reverse also. It could be that we don't detect anything for 30 years, where you can adjust and give the assurance to the asset owner that the structure will last long beyond the design life. So it gives us a field method of validating the design life, validating the service life based on actual data. Now, this methodology has been tested extensively in the lab through accelerated test methods. A lot of that was done in a nearby lab here at the American University in Dubai. So we did a lot of accelerated testing along with Dr. Nagy, where we look at different things. One of the things, well, first of all, we validate that the data that we're getting reflects reality. So we've done testing to do that. We also have run testing to validate that the sensor will continue to give us the data throughout the service life. Because a sensor that you embed in concrete, you want to make sure that it has the life of the functional life of the concrete. And so we're able to run the full cycle where corrosion happens at the two sensing elements and the rebar, and we're still getting information. Another thing that we do, and then we break the samples to uncover the specimens, the sensors, and validate that what we're getting is actually correct. We also did benchmark testing versus the standardized reference electrodes. So in this case, we cast specimens using the ASTM-G109 methodology, concrete beams instrumented with our sensors and with the silver chloride reference electrodes, and data was collected over time. And these specimens were subjected to varied exposure conditions, wet and dry. These graphs here show the results from one of the specimens, where you see how when it was wetted, potentials start shifting. The light blue line is the pulse sensor. The dark blue line is the silver chloride. And you see how the correlation is quite tight between the data that we're getting and the standardized. This is another specimen here. Again, the correlation that was calculated from 0.77 to 0.87 between the data that we're getting, which is considered to be strongly correlating in the Pearson correlation methodology. Moving on to sensor distribution. How do we decide how to distribute the sensors in a project? So we consider the consequence factor and the occurrence factor. So consequence, how severe will the consequence be of any failure? And how likely is this failure to occur? And we look at monitoring zones, selecting monitoring zones based on the criticality of the structural elements, criticality of the exposure environment. We don't place corrosion monitoring everywhere. Wherever you have corrosive environment, it would make sense. So substructures exposed to saline groundwater, marine, coastal environments, that's where you would consider having corrosion monitoring. Then we take into consideration accessibility for inspection. So areas that are not easily inspected, it makes sense to monitor. And ultimately, the decision on where to locate the sensors, we also considered the detailing, the joints. These are the weak areas usually in structures. This is where failures start. So it's very beneficial to know when things start before they propagate beyond those initial stages. And then we deploy the sensors, connect them to the data acquisition hubs that collect and transmit the data. Data transmission most likely happens wirelessly. We have multiple ways of communicating with the data acquisition hubs. LoRa is a common method used in IoT in general. Bluetooth, Wi-Fi, GSM, depending on where the structures are, you could use different protocols for data transmission. In certain cases, wired connection can be used. In industrial settings, they tend to prefer that because of the noise that may be caused by other operating environments. Ultimately, what we care about is the insights. And this is what we get on the platform. A good platform provides us with analysis and modeling of the data that we're getting from the sensors. System notifications are critical. The platform, a durability management platform, is not something that one's going to be watching every day. It's not the stock market. It's something most likely people will forget about until one day you get a notification. So it's important to have notifications that alerts us. You double click on the notification, you go to data visualization, you can see a heat map. Where is the problem happening? How deep is the problem? Move on to the predictive analytics. Okay, I'm seeing an anomaly in a certain area. When do I expect the rebar to start corroding? What can I do? You start considering interventions. And one of the key important things is interoperability. We live in an era where everything is being digitized. Building management systems are gaining traction, and more people are using building management systems. And digital twins are the hype now. I wouldn't say hype because there's a lot of value to digital twins. They're growing in adoption. So what is a digital twin? Digital twin is not just a 3D model of physical asset. It's a live model of that asset. It gets data from the asset. Energy consumption, water management, elevator management, so many different things, traffic management within a structure that can be reflected on a digital twin. And also structural health monitoring can be reflected on a digital twin. Now, digital twins there's a maturity level for digital twins that's known to be at 5 levels, starting with level 1, which basically is collecting the data about what's happening in a structure, the as-built twin. So it tells us what's happening in a structure. The next level of maturity tells us why it happened. It gives us some interpretation, some analysis of what is happening. The third level is predictive, where it tells us what will happen based on the data that we have. What can we predict? Then it moves on to what should happen. What should we do? This is the prescriptive analytics and proposing interventions. We're not exactly there yet, but with machine learning, with AI, and with a lot of data, we're going to get there. And ultimately, the intelligent twin is where you control the intervention, where you automate actually the intervention. This is possible in some solutions like cathodic protection for concrete structures, but as robotics develop and so on, maybe one day we will have a fully responsive twin. It's always important to think about, okay, if I detect something early, what can I do? If it's something like a substructure, can I do anything? What options are available for us? There are multiple early intervention options. Sometimes if we discover something that's happening around a joint, it could be as simple as a joint repair that's needed to prevent much bigger failure in the future. Using migrating corrosion inhibitors that can be surface applied when we know that the chlorides are going through, but initiation has not started, You can use migrating corrosion inhibitors to increase the chloride threshold and defer the initiation of corrosion. Using sealers and coatings to delay the ingress of chlorides. Resin injection. In many cases, we have failures in basements, and we wind up injecting everywhere. If we can determine where the problem started, if we can determine the real root cause of the problem, that can guide us in making those decisions in repair and having more effective repairs. I want to double click a bit about cathodic protection because that is an option for substructures. That's sometimes the only option for substructures in terms of intervention in the future. Cathodic protection is an electrochemical method of intervention of protecting steel. And there are four components to any CP system. There's the monitoring, the actual corrosion monitoring. There's the rebar continuity, assuring that the rebar is all continuous. There's the anode, because cathodic protection basically is making our rebar the cathode. So you need an anode. And there's the power supply. If we can introduce the monitoring along with the rebar continuity, which can be done during construction, that makes the structure ready for future cathodic protection if and when needed. Some install CP from the get-go. In some cases, maybe that makes sense. But it definitely makes sense to prepare the structure for the possible future intervention with CP for substructures where there are limited options in the future if there are any issues. I'd like to share with you last 25-year case study. We don't always get to revisit projects after so long and get insights from a monitoring system. This is a critical structure in Dubai, shipyards in Dubai, very aggressive environment, not only because it's marine. You have special exposure here when the vessels come into the dock and they park here to be repaired. A gate closes. If you see the dock next to it, this is dry because the gate closes and they drain the water out. So you have an area that is one day fully immersed in seawater and then it's fully dry, a lot of oxygen. So you have that cyclic, the most aggressive exposure, the cyclic exposure to salt water. And they had this was built in the late 70s, early 80s. They had major failures in the reinforced concrete. And early on, they did a repair project. You see some of the extent of damage. And they resurfaced a lot of the structures with good quality concrete, very durable, to give it long life. 25 years on, and we're approaching the 50-year mark for this facility. The client is interested in operating beyond the 50-year design life. And so validating the structural integrity and making sure that the structures are safe to continue to operate, they did an investigation. And luckily, 25 years ago, they had the foresight to install corrosion monitoring in their structures. So what they installed is a cluster combination of three types of monitoring devices. There's the reference electrode, a silver chloride reference electrode. There's a coupon, very similar concept to what we're doing with our sensors, let's say an early generation of what we're doing with our sensors. And there's an ER probe. I mentioned electrical resistance probes that measure corrosion rates. So they really have a robust corrosion monitoring methodology. The limitation is that the data was collected manually, and after time, they stopped collecting the data. So we went in and did an inspection for this structure, an inspection for the system. And we had multiple learnings from this exercise. The first learning is we validated the sensor functionality, that after 25 years, we were able to get some data from the coupons, from the reference electrodes, and from some of the ER probes. We were able to confirm the drift that happens with the reference electrodes. The data has drifted all over the place. And the challenge was it didn't drift in one direction. It drifted positive, negative. So it drifted all over the place. We were able to recalibrate, but still that requires continuous recalibration. The coupons provided us with the biggest insight. And the coupons were able to identify a specific type of corrosion, macro cell corrosion that is occurring, where the repaired areas were protected. The areas that were repaired were in good condition, but the areas that were not repaired, the areas that are in anaerobic environment, were acting as the anode to the repaired areas. And so we were getting this, and we were only able to uncover this through having a monitoring system. A surface inspection wouldn't have uncovered this. And this allowed us to have that accurate assessment of the durability dynamics and allowed us to support the client in remedial action prioritization, because in operating plant, remedial actions are very disruptive. So you want to schedule them, you want to prioritize them. And additionally, we're upgrading the system to introduce additional clusters, remote monitoring capability, and platform for real-time monitoring to provide that assurance moving forward about on the integrity of the structures. So in summary, real-time monitoring has general benefits to the asset owner in enabling predictive maintenance, which is more effective, cost-effective, and can be planned, ultimately extending the asset life for the asset owner. Another advantage that's specific to structural engineers, I would say, is the validation of design. So design validation as a goal by using structural health monitoring. Real structures rarely behave exactly as predicted by design due to material variability, load combinations, construction tolerances. What we get in reality is not what is on the drawing board. Structural health monitoring bridges that gap between theoretical design assumptions and actual structural behavior. And these insights provide a feedback loop to structural engineers in designing future structures. Continuous monitoring provides data to confirm or challenge design models, and insights can lead to model calibration, improved safety, optimized future designs. So I invite you all to consider structural health monitoring, durability monitoring specifically in your future projects, and I'm happy to take your questions.
Thank you very much, Osama. Very insightful presentation. I liked your analogy with the human aging and the importance of early detection.
Yeah.
Let's start with questions from the room. Any questions here? Dr. Shapoor?
So this cost
Cost. Good question.
and the time required before you can, at what stage should be approached? How much does it cost for implementing and monitoring it? Assuming it's in 25 years, I'm going to continue monitoring in 25 years time yourself?
Good question. So in terms of cost, the answer is it depends, of course, on the structure, but I'll give you some sense of what that is. And the involvement starts from the design stage. So from the design stage, when the client is decided to have monitoring, we review the drawings, we look at the exposure conditions, and we make a recommendation on the distribution of the system, the sensors, what data acquisition hubs are required, and so on. And from that, the cost is derived. To give you just a ballpark, for a typical building, it could be anywhere between $50,000 to $100,000 to $150,000 based on the dollars, based on the size of the structure. In infrastructure, you're going to go beyond that. Just to give you an idea about costs, but it really depends. It really depends. Mainly focused on foundations, unless coastal marine environments, there are structural elements that are exposed to such environments. And then this cost is for the deployment of the system. What we do is we provide the hardware, we oversee the installation. The installation is done by the contractor, but overseen by us. And then the system is commissioned and you get a subscription to the platform. The And the platform is accessed by the client, and you get the insights and the data from that platform.
But who's going to be there in 25 years?
Who's going to be there in 25? Hopefully, we will be there in 25 years, and the platform will be there in 25 years.
Saying that went to a project, and after 25 years, none of those people who installed are there.
The critical thing there is that it's manual. Like you have to have data collection. It's manual. It's entered into an Excel sheet. It's not like the hard work in this is installing the system. Then the system does the monitoring.
Perhaps there should be kind of a guideline for building operators to somehow continue monitoring by their own, to some extent, interpret the data. Is it possible, do you think, or it needs high expertise to do it?
The platform provides that insights, so it doesn't require expertise to really interpret the data. The platform provides you with that, so they have access to that.
This knowledge is transferable, you said, to operators, or it's just
the platform
complexities for some cases.
No, the platform is easily managed in terms of getting the insights. Now, when the client wants to decide what interventions they want to do, that's when they involve consultants for that. So in terms of the interventions. But in terms of knowing the health of the structure, knowing if there are issues, where are these issues, at what depth these issues are, that information is there for them. Yeah, but as I mentioned, the maturity levels of the systems, we're at the predictive. So those predictive insights, the clients will have access to from the platform. But when you go to the intervention, which may be something that we get to in the future as we start looking at a lot of data and machine learning and all of that, so that could be future iteration of the platform. But currently, we're looking at the insights are at the fingertips of the owner.
Protection, to revise the rebars and basically arrangement of rebar or connectivity of rebars when you have a protection at the one side of a beam or one side of a foundation. You make sure that this kind of electron exchange continues in different.
You're asking about cathodic protection. Yeah. For cathodic protection, you need to have the continuity, which is usually there. But during construction, what's important to pay attention to is wherever you have joints, wherever you have, so these are areas where continuity needs to be assured. So
you have some suggestions for this.
Yeah. To have that provision for future intervention. Yes.
Suppose during engineering, I may incorporate this device. And my meeting has 5 years already performed. And now I want to find that my client takes decision. Do you want to install as monitoring system? So is it possible?
To retrofit?
Not retrofit. Okay, now like after hearing this knowledge session, I told my client like this is a facility available nowadays, and we should go for this. So building is existing. So is it possible to implement?
So it is for an existing building where you need to, you'd be limited in using these sensors, the early prediction. It is possible to do it with some of the other corrosion monitoring sensors. So it's something that we could look into. As always, designing something in is easier than retrofitting in the future. So this is why the answer depends on that particular situation. So monitoring is possible, but you need to look at the details.
Building is 25 years old, and I'm doing retrofitting. Like I'm providing CP system and doing all precautions. Maybe I have taken out concrete field, rebar labor. So at that stage, is it possible?
It's possible, but let's look at the details to see the extent.
Thank you. We've got 2 questions from Zoom. The first one from Hatim, an excellent question. For ordinary or standard structures that are already designed with generous safety factors, and can be adequately maintained through routine inspections. How do you justify the cost and practicality of installing a structural health monitoring system? In such cases, would you think the monitoring system would become more of a luxury than a necessity?
Good question. Inspection, but I go back to the value proposition that I shared. Like inspection is limited in what it can tell you. If you are confident in I think the challenge with construction is that it passes through multiple stakeholders. You can have the perfect design, but then it goes into implementation. You have the contractors involved, you have multiple suppliers. It's a very complex process. So to get it perfectly, like this assumes an ideal world where it's perfect and the aging process is not so if there's no problem, there's no need to fix it.
Yeah.
But we don't live in an ideal world, and we know that structures do age, and we live in a very aggressive environment. And so the necessity to know things early, the value in that, avoiding it's like insurance,
Yeah.
avoiding any major issues is there. That's the value.
You've probably touched at it in the beginning on the importance, the criticality of the structure itself. How important is it to invest in these additional things for proactive maintenance? The second question, I'm going to read them for the YouTube recording. The second question is from Amit Ranjan. When to take action during construction? During construction or after 25 years when the problem starts?
Who ideally you want to install the system during construction?
Yes.
Yeah, from the get-go.
I think the action maybe means remediation. Not sure. Yeah, maybe. Yeah. So installation definitely during construction. Yeah. Any more questions?
It is not a question, just I would add, one of our client, he was aware about the industrial environment, and during design stage only, all the files which were taking critical structures, they were cathodically protected. And this information helps us to monitor every year. There is no corrosion happening with the pipe, who are taking the superstructure load down to the earth.
Yeah.
This works and it gives confidence.
Thank you for the insights.
Yeah, having an active, some clients opt to have an active cathodic protection from the get-go. Another option is to have the monitoring and continuity, that if the monitoring informs you there's a problem, then you invest in the cathodic protection system. So there are two approaches, two philosophies. Yes, please.
This kind of anxiety stays with me from Corona time. When people talk about corrosion in higher elevations due to chlorine in the air. Is that serious to be worried about?
I'm not
serious, then I have to be careful about monitoring the higher elevations, and because the cost will be extended.
I haven't come across that being a serious consideration for structures. Maybe I'm not aware of it, but I haven't come across it from my exposure to the industry.
Or concrete in touch with soil or groundwater.
Unless otherwise, if they start having snow and they use the ice and salt in this country,
Yeah.
Not an issue like this here.
Not that I'm aware of. Dr. Nagy, are you aware of it? Have you?
I'll go check the cloud seeding if there's any risk.
Yeah.
Yes, please.
What do you think would be the way to encourage thinking about corrosion monitoring for not only those people who are actually owning the building, like government organizations or those companies who build a hotel that are going to look after, but also for the buildings that the developer is building and then selling it to so many different people. What do you think would be a way to encourage this, that all the building developers or construction people to start thinking about corrosion? What would be the way forward?
Population, maybe.
What is it?
Regulation.
Regulation would be helpful. Regulation would probably be the only way. We've had conversations with all sorts of clients, and we get that pushback where clients sell and they're not going to be monitoring. And sometimes that's I think it's a matter of awareness. It's a matter of understanding the extent of the issues, but it's a challenge.
People are usually convinced by evidence, so I might suggest, and that will come with time, so that is probably a few years old now. These case study that show, doing a full remediation replacement without the sensors, and having the sensors has actually, I put this much to do the predictive maintenance and compare the cost and tell the owner, look, this is how much you save with this little investment. So these case studies, I think, could land nicely with the building owner if we could have them from local examples.
Those people who actually own the building have no problem listening to this. Problem was those people who built the building and they sell it to so many people. So the interest of the ultimate owner is not there at the time of design and construction.
They are not worried about their legacy and their brand.
It's short-term benefits.
It's a challenge, but there is the reputational aspect. Another way of convincing some of the developers they buy into that this is a smart building, so marketing that, and so that's another way. But the genuine interest and the longevity of the structures, it's a challenge when somebody doesn't fully own it. Regulation would be the best way to make it. Just one thing I'd like to add, if you allow me, that we're looking at design life of 50 years for buildings. According to Dubai building code, 50 years goes up to 75, 100 for tall structures, tall buildings. But in the life of cities, this is nothing. Like, we may not feel it now, but when you look at cities, like the older cities of the West, the infrastructure is falling apart. We're not feeling it now. We're still a young city. And it's important to learn from other people's examples and implement that here to really have a city for the future. So, like dry docks, 50 years have passed. Now they're looking at, okay, we designed this for 50 years, but we want to operate for at least another 50. How do we get that assurance? So that's the foresight that's not always there, but I think with awareness, hopefully we'll get there.
In green building construction, we have insulating stars or gold, platinum to somehow give the impression to the consumers that this is a high quality service or low quality. Is it possible that the building durability is certified by some third parties? Not necessarily you, because of that is, so I'm in charge of the project, so of course I would like to certify it for longevity.
Yeah.
But is it possible to have a third party to certify it and somehow commercialize this? This contractor or this construction company invested X% additional on durability of building, and someone is certifying it. Then this certification is a good feature of the building to have higher price and be economically valuable.
That's a good suggestion to consider and discuss. So
Save apply on lead. Yeah, have it certified.
Add a score credit to lead, maybe.
Yeah.
Here's a few good ideas to go back and think about. It's a little bit of a burning question, Osama. You've seen so many dashboards and you've looked at so many data. Did you see anything that surprised you? What did you learn from this? I mean, there's the normal aging of concrete, the things that you expect, but there's always the unusual thing that surprises you. Oh, I wasn't expecting this. Is there anything that happened or not yet?
From the dashboards, well, what I shared about the case study, like, we were surprised by the outcome of what we uncovered, the dynamics, the corrosion dynamics that we didn't expect, which were not the typical, that they were getting macrocell areas that were repaired. So if you inspect the structure, you will find that it's in good condition, but what's happening beneath is beyond what's inspectable is what was the problem. So that was a surprise, and we were able to get that through having
Yeah. Maybe with time we can enhance the way we build things from the beginning by listening to the data, what the data tell us.
Yeah, I came across a paper about specifically durability modeling, service life models, that they're based on first principles, Fick's second law of diffusion, and they're based on empirical data from labs and from the field. Less than 15% of the data, the empirical data, is actual field data. Everything else is lab data. So as we get more and more from the field, I'm sure that's going to inform us to design better and
Good. There's no more questions on the platforms.
Okay.
I wish to thank you very, very much for a very insightful presentation. And again, thanks to Dr. Payman for your hosting us tonight. And our audience also, thank you for joining us. Our next CPD event will be on the 18th of November, also on sustainable concrete. So we will continue the discussion then. Thank you very much and good evening to everyone.